So let's start with a problem. Now this particular problem was actually off of a recent exam. And the students did not like this problem, which, surprised me. And after the exam, they went and then they worked on their homework and they discovered it was just like a homework problem. It pays to do your homework. Now, I am not saying that the homework problems are like the exam problems this time. I don't know. I haven't looked at the homework problems in months. But it does pay to do your homework. So here we go. You have just attached a 4-foot tall TV to your wall. Now you might be thinking, hold on a second, this does not seem very realistic. I'm a college student. I can't afford a wall, but it's okay. All calculus problems are like that. It's just some crazy scenario. All right. So you have a 4-foot tall TV attached to your wall, and the bottom of the TV is going to be 7 feet above the floor. Now when sitting on your couch, your eyes are 3 feet above the floor. The question, how far back from the wall should the couch be placed, and we call that x, in order to maximize the angle theta from the top of the screen to the bottom in your field of view? And it says include units in your final answer. There is a note here that for this problem, you do not need to verify that your answer is a maximum using a first or second derivative test. Now, sometimes we will say you do need to verify, so pay attention. If a problem says, explain why this is a max or min, or justify that this is a max or min, make sure you actually include that part. If you don't, then you won't get full credit for the problem. So this is trying to optimize our maximum field of view. This is a problem that people often encounter when they go to a movie theater. They want to find that sweet spot, the one where they get the most view of the screen. So our goal is to maximize theta. So what do we want? Well, with every optimization problem, it always boils down to one thing. You want to express what you're trying to optimize in terms of the things that you can vary. Now, in our case, what we're allowed to vary is x. So we want to figure out, okay, how do we express theta in terms of x? Well, one way to get to it is to say, all right, I'm really good with theta when I have triangles that are right triangles involved, because those are the right kind of triangles to work with. This theta right here is not looking like it's coming out of a right triangle. But here's what we can do. We can take this dotted line, we'll fill it in, and think about there being two right triangles. There's one right triangle which is sitting here, and then there's a bigger right triangle, which I guess I happen to have brought pens with more than one color today, so I will mark there's another right triangle that's sitting there. And what I can do is I can say, okay, let me figure out what the angles of those two triangles are, and then if I take the difference, that's theta. So I can say that theta, the thing that I'm trying to optimize, well, let's start with this big triangle. Well, we know this side is x. Now we think about, okay, what's this? Well, I'm 7 feet to the bottom of the TV, so that means I'm 11 feet to the top of the TV, but I had to go 3 feet up. So if I were to really break things down, I could break this 7 feet into 3 feet up to my eye line, then 4 additional feet, and then 4 additional feet on top of that. So that this length here is 8. So if I look at my two sides, I have 8 is my opposite side, and x is my adjacent side. What relates those two things together, opposite and adjacent? The tangent. So if I think of this big angle here as being my alpha, I could say that tangent of alpha is equal to 8 divided by x. So that my angle alpha is arctangent of 8 divided by x. All right, so that's my big angle. Now I have to subtract my smaller angle. So my smaller angle, that's the one in the smaller triangle. Here, I'll call that beta. And it's a similar process. The only thing that's changed about this triangle is instead of 8 on the opposite side, it's 4. So I get tangent of beta is 4 over x, so that beta is the arctangent of 4 over x. And I'm going to subtract that angle off. And now, if you give us any x value you want, we can say exactly what our angle is. So we've expressed what we're trying to optimize in terms of what we can vary. And once you've done that, you've done pretty much the hard part, because this is the translation of words into a formula. And once you have a formula, it's like, hey, I'm back into my comfortable place where I know how to work with this problem. In particular, we say, all right, if we're trying to optimize, then we take derivatives, because we're looking for where the critical points are, because the critical points are very helpful for identifying max and mins. So take the derivative. I'll call it theta prime. Derivative of arctangent of 8 over x. Well, arctangent, derivative of that is 1 over 1 plus the inside squared. Do we need to do anything else? Yeah, times the derivative of the inside. Now, the derivative of 8 over x. Do you know what that is? It'll be negative 8x squared. Because you can think of the over x as being x to the negative 1 power. So if you have x to the negative 1 power, you bring the power down. That's where the minus comes from. Subtract 1 from your power becomes x to the minus 2. Yes? All right. All right, good. So we're going to subtract now, a similar process, 1 over 1 plus 4 over x squared. Okay, 1 over 1 plus the inside squared times the derivative of the inside. That's going to be negative 4 over x squared. Well, this looks like we're going to get to do some exciting algebra. Okay, so here, the first term, that's negative 8. And downstairs I have 1 plus 64 over x squared multiplied by x squared. So as I squared this term, then I just have the x squared going to the bottom, negative 8 going to the top. Then over here we'll have plus 4. And downstairs we're going to have plus, because minus minus, 1 plus 16 over x squared. And that's being multiplied by x squared. So you multiply the x squareds together, or I should say maybe distribute them through. Negative 8 over x squared plus 64 plus 4 over x squared plus 16. Now, what do we want to do? All right. We should probably do algebra. Here, common denominator. Add them together. So, negative 8 times x squared plus 16 plus 4 times x squared plus 64, and divide that by x squared plus 64 times x squared plus 16. Well, we're getting close. So negative 8x squared, and 8 times 16 is a number, yes, minus 128, plus 4x squared, and 4 times 64, that's another number, 256. And I hope we're almost done, because we're running out of space here on the page. Well, minus 128 plus 256, that's 128. And then minus 8x squared plus 4x squared is going to be minus 4x squared all over your denominator, x squared plus 64 times x squared plus 16. All right. We're pretty much ready to talk about theta prime now. We simplified it about as far as we want to go. Now, what can we say? Well, looking at this, we can certainly say that our derivative is never undefined, because there's no part where we divide by 0. That's one of the nice things about the arctangent. It's 1 over 1 plus something squared. You're not going to divide by 0. So if we're looking for a critical point, where do we look? Well, we look for where it equals 0, and that's where the numerator equals 0. Okay, so we need to set our numerator equal to 0. So we're going to focus our energy here. So we're going to get a critical point when 4x squared equals 128. Well, divide by 4, x squared equals 32, which means x equals the square root of 32. And, well, that's our only one. Of course, we could say, what about negative square root of 32? That's probably not going to be a really good idea. You'd have to sort of like drill a hole through the wall. And you're probably not going to be able to see it very well since the wall is going to block your view. So yeah, the positive square root of 32, we can use intuition to rule out the negative. And so our final answer, because we only found one, and it has to be the right one, we don't have to verify it. So our final answer is the square root of 32 feet. Because it does say include units. How do we know it's feet? It's because all of our other measurements were in feet. So that's how far back we should go. Now, if you're wondering how big is the square root of 32, well, square root of 32 happens to be 16 times 2. And 16, square root of 16 is 4. And the square root of 2 is about 1.4-ish. So about 6 feet. Seems a little close, but that's all right. Okay, and there you go. All right, any questions before we get on to today's topic? Well, let's get on to today's topic. So today's topic, it's a beautiful idea. And it's called Newton's method. Now, Newton is, he's somebody who we often associate with calculus. Of course, the thing that really Newton is best known for is not necessarily the ideas of like, oh, let's look at things how they change, or let's look at things and how we add them up. Newton was the one who sort of said, hey, let's look at how these things combine together, which we're going to talk about in a couple of weeks. But for now, we're going to look at a very particular problem. And our goal is we have some function and we're after a root. So a root is when we have a function where f of x equals 0. And we're like, I want to know when does this function equal 0. Or at least I want to know a really good approximation to it. And so what's the idea? Well, the idea says, it's easy to find roots of lines. Lines are super easy to work with because they're flat, and we love them. So what we can do is say, well, let's take the curve which we can't understand very well because it's complicated and it's bendy, and we're going to focus on our straight lines and see how they can help us. So here's the picture. We say, look, I'm after the root. So this part over here, this is the goal, the root. That's what we're after. And here, this is where we're at. This is our current location. And we'd like to jump straight to the root, but that's very hard. Finding roots is actually an incredibly hard problem. In fact, mathematicians spent hundreds of years to come to the conclusion that it's hard. And it was a big achievement when we actually figured it out. So much celebration was had. So, but how do we say, okay, what do we do? Well, we say, all right, here's our current guess. It's probably wrong. So how do we make a better guess? We say, all right, well, we come up to the function. We say, all right, here's our point on the function. And we can take the tangent line to the curve. Now, why do we do that? Well, the function itself will do whatever it does. But the tangent line, we can follow the tangent line down. And because the tangent line mimics the function nearby, it's going to be a fairly reasonable guess if we were close. So that what happens is we get to a new location, which is our better guess by following the tangent line down. Now you might say, okay, then what do you do? Well, what do you think we do? Do it again. You take your better guess, and you find that tangent line, and you're like, wow, that's even better. But maybe it's not good enough for you. So what do? So you do it again. So it's all about sort of better and better approximations as you repeat the process. So let's see what happens. So suppose that our current guess happens to be here. Let's say this is at x equals a. Well, we know how to find the tangent line at x equals a. This is something that we've done for a while. It's the same thing as the linearization. It's f of a plus f prime of a times x minus a. So we're going to figure out where does that tangent line hit the x-axis. So that would be when we set y equals 0. So we hit the x-axis and y equals 0. So, okay, you set y equals 0, and you do a couple of things. You can subtract f of a over and divide by f prime of a, and then you would add a. And if you do that, none of this algebra is tricky. You say, here's your next guess. So to go from your current guess to your next guess, it's a very simple formula. You take your root a and you subtract the function at a divided by f prime of a. Now, one thing you can do to sort of convince yourself that this is actually a reasonable answer is, let's suppose you happen to magically get a root. So suppose that a were a root. What would happen if you plugged a root into this formula? So if a is a root, what's true about f of a? It's 0. Which means that when you have a root, it says, no, don't move. You've already found the root. Don't change. So that's a way to convince ourselves, well, at least it's a somewhat reasonable thing to do. So here we go. Here's the process. We start, we say, what's our initial guess? Now, the closer to the root we can be, the better. Because the closer you are to the root, the faster you're going to converge to the answer. What do we do? Well, we repeatedly apply this idea of using the tangent lines to get a sequence of better guesses. So you'll notice that there's a subscript here. So the subscripts indicate which guess you're at. We oftentimes like to start counting at 0 because computers seem to like that. So x sub 0 says, this is my first guess, my initial guess, my 0th guess. x1 would be what would happen if you did it once. So if this were x0, this would be x1. x2, now you run x1 through the process and you get x2. And then you'll keep running the process on and on and on. And then you stop at some point. Well, when do you stop? Well, you stop when you've, say, gone a certain number of steps, or you see, well, my answers aren't changing significantly, so I must be very close to a root. Or you stop if you see something going on. We'll talk about things that can happen that might occasionally wreck the machinery. But that's okay. Most of the time it works pretty well. So let's do an example, just to sort of get an idea of how this might work. So let's use Newton's method to approximate square root of 2. Now, you might say, hold on, you're missing stuff. Because Newton's method says I need to find a root. And I'm saying, look for a number. Well, so what does that mean? Well, that means I need to find a function where when I plug square root of 2 in, I get 0. So what's our goal? Well, initially our goal is we want to find some function f of x so that f of square root of 2 equals 0. Because I need to find a root. This is a root finding tool. Now you're probably thinking, I know of a great function that does that. Here's the function that does that. X minus root 2 does that. Right? Because if you plug in root 2, you get root 2. If you plug in root 2, you get root 2 minus root 2, which is 0. It's like, but that's not a really good function to work with. Now, why do I say that's not a good function to work with? In order to work with that function, what would you need to know? You need to know square root of 2. And if you already knew square root of 2, why would you be looking for it? That's a crazy thing. Okay, so that's not necessarily the function we want. So it's not going to be that one. So we're looking for a different function. Well, can we think of another function which maybe has nice numbers that we do know, we're comfortable with, that when we plug it in, square root of 2, we get 0 out? Sorry, what? X squared minus 2. Aha! So, f of x equals x squared minus 2. That is a function where the things that are already in there, 2, that's something we know what it is, and that's something we can work with and be comfortable. So this is a good function to work with if we're trying to find square root of 2. Okay, well, so now we have our function to work with. So the next thing we need to do is to really write down this pattern. So I'm talking about this pattern right here. So we're going to take our xn plus 1. I'll write it down here again for reference. xn plus 1. That's equal to xn minus f of xn divided by f prime of xn. Now, in our case, that would be xn minus, when we plug it in, on the top we'd have xn squared minus 2. On the bottom, what would we have? Well, derivative of f of x is 2x, so you plug in, you get 2 times xn. Now, that's perfectly fine. The other thing you could do is play around with this and clean this up. For instance, we could say that this is xn, and on this term, suppose we break this up. So that's minus xn squared over 2xn, which would become minus xn over 2. So I'm just taking the xn squared divided by 2xn. And then there's a plus 4 over 2xn, which would become a plus 2. Sorry, not a plus 4, a plus 2 over 2xn, which so that becomes a plus 1. Whoops, plus 1 over xn. And if we put the first terms together here, we see this becomes xn minus xn over 2 is xn over 2 plus 1 divided by xn. So that says if I have a guess, divide it by 2, and add 1 over the reciprocal of the guess, and that should be a better guess. So let's see if that actually works. Okay, so let's start with x0 equals 1. What would x1 be? Well, if we apply this, and by the way, you don't have to simplify. If we had plugged it into here, you'd still get the same answer. I'm just simplifying because I want to talk about this form in a second. So it would be 1 over 2 plus 1 over 1. Well, 1 over 2 plus 1 over 1, what's another way to write that? Yeah, 1.5. 3 halves. Okay, well, is 3 halves a better estimate? Well, I said square root of 2 is about 1.4, and 1.5 is closer to 1.4 than 1 is, so that seems like a good sign. Okay, let's talk about x2. What would that be? Well, we're going to take half of the current estimate, so that would be 3/4, plus, now flip it over. If you flip 3/4 over, flip 3 halves over, you get 2/3. Okay, if we wanted to add these together, what would be our common denominator? 12. So it's something over 12. Now, let's think about what that would be. Well, in the first term, we'd have to multiply by 3, so that would be 3 times 3, which is 9. The second term would multiply by 4. 4 times 2 is 8. So add those two together, you get 17. Okay, 17/12. That sounds closer. Now, on a side note, you could actually square these things. If you squared 17, what would you get? You get a number, yes, 289. If you squared 12, 144. So if you multiply 12 squared times 2, 144 times 2 is 288. Really close to 289. Coincidence? No, because we're getting really close to square root of 2. And these values are getting closer. Suppose we went just a little bit further. I don't know why. I'm going to regret this choice in a second. But, all right. So what do we have? Well, 17/12 divided by 2, that's 17 over 24, plus, flip it over, 12 over 17, equals something. All right. Yeah, like I said, I'll regret it. Okay, but you can get a number there. And you'd play around with it. Let's see. Do we want to try to get a number here? Wait, what? We do? Well, 24 times 17 is, of course, 408. Is it? I don't know. I just heard somebody say that, so it might be true. Okay. Does anybody know what 24 times 17 is? 408? Oh, good. Whew. Okay. All right. Now, The next thing is you have to take 17 times 17. Well, we know what 17 times 17 is. We just talked about that. That's 289. Then we have to add 12 times 24, which is 288. So if you add 289 plus 288, that would be 577? Was that close? Yeah. 577? Okay. All right. So somebody check what 577 divided by 408 is? 1.4142? Okay. Now, what's the square root of 2? 1.4142? Now, this is not the square root of 2. I don't want you to walk away thinking, aha, we just found the square root of 2. But what we've done is we said, look, in just a couple of steps, we found something which is really close. So that shows you that this idea of better and better approximation pays off. In a modest amount of time, we can find something which approximates square root of 2 fairly well. 17/12 is actually probably more than enough for most purposes here. Now, one of the reasons I point to this particular example is that people have been really interested in the square root of 2 for thousands of years, way, way before Newton was born. They were looking in the Middle East, they were looking in ancient India. They wanted to look at mathematics. And they actually had this idea of successive approximation and getting better and better. So the ideas of calculus are not somehow the results of something that happened in Europe a few hundred years ago. The ideas of calculus, it's part of humanity. It belongs to everybody. So it's beautiful, beautiful. Now, a couple of notes about this method. We are not going to find roots. Unless something really weird happens, we never find a root. What we're always about is trying to get better approximations to that root. And oftentimes, for engineers in particular, that's good enough. We just need a good approximation. Now, suppose you do find the root. Does that mean it's the one you wanted? The answer is no, because oftentimes functions will cross an axis multiple times. So if you're after a particular solution, you have to make sure that you want to start near that solution. If you just start in a random place, if it converges, it'll converge to some root. It may not be the one you want. So if there's something you're looking for, make sure you start close by. Now, how do you get close by? We'll talk about that in a few minutes. This third point, this is highly computational. Because there's lots of things you have to chug away at. Make it, do this arithmetic and make it work. So what does that mean? Well, it's best done with things which love doing computational things. So in other words, this is great for computers, not so great for humans. And so you might be wondering, well, what does that mean for us on the exam? The answer is, it often means we'll say, set it up, or we'll say, here's x0, find x2. So you're not going to be expected to be like, find x100. That's not going to happen. Just need to be able to set it up. That's the main thing, and then just run it one or two steps. Now, the last word of warning. Things can go bad. And what do we mean? Well, suppose here's our axis here, and we have a curve. So perhaps we have a curve that's, there's a lot of roots that we're after. And we might be saying, okay, we're not paying any close attention to something. And we'll say, let's put our first guess here. And the reason why I'm saying this thing is like, we're after that solution. Well, notice what happens. If we make our first guess, we shoot up to the curve, and then we take the tangent line. But what's true about this tangent line? The slope of it. It's very small. So what ends up happening is it shoots you, and your second guess goes way out. And then, of course, you get here, and that tangent line is also shooting you. It's going to start moving you all over the place. So you have no idea what happens. if you end up with getting a place where f prime of n is very close to 0. So whenever your derivative is close to 0, things can sort of get messed up. So just be careful. And the best thing to do is try to get close to your root. And if you are close to your root, things tend to work out fairly well. Okay. So let's do a little bit of practice. Okay, let's do the next problem. Use Newton's method to approximate a root to y equals x cubed plus 7x minus 3, starting with x0 equals 2. Give the exact value to x3. Well, that means we're going to do it 3 times. All right. Well, so what do? No surprise. We should start with our basic formula. xn plus 1 is equal to xn minus f of xn over f prime of xn. Well, our function is this function right here. So f of xn is xn cubed plus 7xn minus 3 divided by downstairs 3xn squared plus 7. Where did that come from? Well, if you take the derivative of x cubed plus 7x minus 3 is 3x squared plus 7. So 3xn squared plus 7. Now, you have sort of 2 options right now. Now, one option is just to go with this as is. The other option is to simplify. Now, given that we're going to go to x3, it might be useful to do a little bit of simplifying once. And, well, then we'll be good. So you can either do a little simplification at the start or a little bit of simplification at each individual step. Sometimes, if you're doing many steps, it's easier to simplify first. Our common denominator will be 3xn squared plus 7. So if we multiply the first term by 3xn squared plus 7, that gives 3xn cubed plus 7xn. All right. And now, the other term, remember the minus is going to go through each piece. So minus xn cubed minus 7xn minus 3. So it becomes plus 3. So if you notice here, the 7xn's cancel. Well, that's nice. And these xn cubes can combine together. So we get 2 times xn cubed plus 3. Divide that by 3, xn squared plus 7. Good. Now that's just the recursion. We actually got to do the work. So, well, let's get to work. So we know what we're starting with. We're starting with x0 equals 2. So there's x0. Now, what's x1? Well, we can plug it in here, or we can plug it in here. These are equivalent. They're just the same way of saying, different ways of writing the same expression. So if we plug into this bottom one, the one where we cleaned it up, what would we get? Well, we'd get 2. Then we're going to get 2 cubed, so that's 8, plus 3. Downstairs we're going to get 3 times 2 squared plus 7. Now, 2 times 8 is 16. If we add 3, that gets us to 19. 3 times 2 squared is 12. If we add that to 7, we get 19, which means x1 is equal to 1. Nice. Okay. That means it's not so bad to keep going. How about x2? Well, plugging in 1, we're going to get 2 times 1 plus 3 divided by 3 times 1 plus 7. Well, that's 5 over 10, which is 1 over 2. Okay. That's not so bad. All right, x3, because it says find the exact value for x3. So that's going to be 2 times 1/2 cubed. That's 1/8. Plus 3. Divide that by 3 times 1/2 squared, a fourth, plus 7. Now, that's really 1/4 plus 3 divided by 3/4 plus 7. And if you take this expression, say multiply top and bottom by 4, get rid of your fractions, what do you have? On the top, you'll have 1 plus 12. Downstairs, you'll have 3 plus 28, giving us 13 divided by 31. And that is the exact value for x3. And we're done. Okay, well that's not so bad. These problems are fun. I mean, it's a little bit, you got to be careful, do the process, work it out. But once you get the process down, no big surprises. Good. Find an approximate solution to the following. X cubed minus x equals 1. Now, right now, this is not a Newton's method problem, but we might say, okay, how can we turn it into 1? Well, first off, there's an approximation. Well, that's good. Newton's method looks for approximations. And we say, okay, but remember, what does Newton's method say? It says we're going to approximate f of x equals 0. So in order to apply Newton's method, we have to be in the right format. Right now, we're not in the right format. So we should make it the right format. So by making it the right format, what we mean is rewrite this in a way so that whatever we're looking for is something where we get f of x equals 0. So the easiest thing to do in this case is say, okay, suppose we were to subtract 1 from both sides. X cubed minus x minus 1. And I'll call this my f of x. Well, look, what are we looking for? We want to have a place where f of x is equal to 0. So this is a root. We're looking for a root. That means we're perfect. Exactly what we want. This is made for Newton's method. Now, there's a question. How do we pick x0? Now, in some sense, well, we can pick it to be arbitrary. But so we should try to choose wisely. So let's think about how we can choose wisely. We'll go looking for where a root could be. So let's pick some values. 0. That's a good value to pick. What happens? Well, if you plug in 0, you'll get that the function is negative 1. That's easy to plug in 0. What happens if you plug in 1? Well, you get 1 minus 1 minus another 1, which turns out it's another negative 1. Okay. What if you plug in 2? Well, you're going to get 2 cubed is 8 minus 2 minus 1. That's 5. If we plug in 3, why not? We have the space. 27 minus 3 minus 1. That's 27 minus 4, which is 23. Okay. Now, if you were looking for a root, then you say, okay, where could a root be? And the answer is, look here, between 1 and 2. Notice we're negative, then we're positive. So we're starting below the axis, we're ending above the axis. So there's something called the intermediate value theorem. And that's the one that says, I can't jump over something. I have to hit all the values in between. So in other words, if I start at negative 1 and I end at 5, I have to definitely hit everything between negative 1 and 5 at least once. I might hit some things multiple times. I might even hit some numbers outside of negative 1 and 5. But definitely 100% for sure, everything between negative 1 and 5 will get hit. So we know that there's a solution in here. But how do we find it? Well, one thing we can do is we can continue probing. We can say, okay, let's cut it in half, and then we'll take whatever we get. If it's, say it's positive, we'd come over here. Or if it's negative, we'd go over there. So there's something called bifurcation. We can split it. And you might be thinking, hey, that seems pretty reasonable. That works, right? You're sort of like cutting in half each time. Wouldn't that work better for finding solutions? And it turns out, no. It's kind of slow. And most of the time, it takes a long time to actually find stuff. So we want to process that as quick. Look, we don't just want an answer. We want an answer we can get to in a short amount of time, because we appreciate both, accuracy and speed. And so when you do this bifurcation, you basically only have to do a couple rounds to improve it by 1 decimal digit. Whereas Newton's method, oftentimes you'll get several digits at once. We'll see an example in a few minutes, sort of highlighting just sort of how good Newton's method can be. Okay, so what's our goal? Well, we think it's between 1 and 2, and 1 is certainly closer to 0 in terms of the output. So let's pick x0 to be 1. So what do? We sampled the data, and we said the intermediate value theorem says it has to be around here. So we have our guess. Now, xn plus 1 should equal xn minus our function f of xn divided by our derivative, f prime of xn. Well, what's that going to be? That will be xn minus our function is xn cubed minus xn minus 1. Our derivative, well, our derivative of x cubed minus x minus 1 is 3x squared minus 1. So we can make a little side note somewhere. We have some, up here. F prime of x is 3x squared minus 1. So that's 3xn squared minus 1. Now, if we clean it up like we did before, might as well, if we're thinking that we're going to do one or more than one term, if we're only doing one term, there's not much use to cleaning it up, but maybe we'll do 2. Let's hope. All right, so 3xn cubed minus xn, and then we're going to subtract, and remember this subtraction will distribute through, xn cubed plus xn plus 1. All divided by 3xn squared minus 1. All right, well, what do we get? Well, the minus xn plus xn cancel out. That's nice. 3xn cubed minus xn cubed becomes 2xn cubed. And then we have plus 1. And then we're going to divide that by 3xn squared minus 1. All right, good. Well, let's start chugging away. So we said x0 equals 1. All right, write that down here again for reference. So what is x1? So 2 times 1 plus 1, that's 3. Then we get 3 times 1 minus 1, 3 halves. Okay, maybe we would have guessed to look at 3 halves. Now, we probably should check to see how these answers compare. When we had x0 equals 1, if we think about this side, well, we'd have 1 cubed minus 1. On the other side, we'd have 1. Well, 1 cubed minus 1 is 0. Well, not really close to 1. If we plug in 3 halves, now 3 halves cubed, well, that's 27 over 8. Then we subtract x, that's 3 halves. Now, if you put that over 8, what does that become? Well, that's 27 over 8 minus 12 over 8, which is, what is that? 15 over 8? Well, again, not very close to 1, but, we haven't gone very far. Maybe the next one. Okay, so x2. Well, that'll be 2 times 3 halves cubed plus 1. Downstairs, we're going to get 3 times 3 halves squared minus 1. Now, if you cube this, you're going to get 27 over 8. But then you have a 2, so that's really 27 over 4 plus 1. And downstairs, we're going to get, 3 squared, 9 over 4 times another 3. So that's, again, 27 over 4, but now minus 1. And what does that become? We'll multiply top and bottom by 4. So it becomes 27 plus 4 over 27 minus 4, which becomes 31 over 23. Okay, well, is that better? I don't know. 31 over 23, that would require a calculator. And so, okay, that looks like a good place to stop. So this is an approximate solution. All right, well, how could we find it out? It turns out that cubics you can solve explicitly. So we could solve it. I think what we would discover, it's not bad. And if you look at this, how does this compare to 3 halves? Well, if you think about 23, you say, okay, if I multiply 23 by 1.5, that's 23, plus an additional 11.5, which would be 34.5. So it's a little less than 3 halves. So we went 1 to 3 halves, and then we're back a little bit to 31/23. I think we're starting to zoom in, and I suspect we're actually getting pretty close when we get to here. All right. Well, let's try another problem. Okay, so the next one. Use Newton's method to approximate a root of f of x equals x to the 5th plus 3x squared minus 9x plus 9, starting with x0 equals 0. So let's write down our basics here. So all right, we have our function, x to the 5th plus 3x squared minus 9x plus 9. We have f prime of x, that's 5x to the 4th plus 6x minus 9. So our basic recursion, xn plus 1 is equal to xn minus. Now we take our function, so that's xn to the 5th plus 3xn squared minus 9xn plus 9, and divide it by 5xn to the 4th plus 6xn minus 9. All right, there we go. There's our basic formula. What do we do next? Well, we could combine it. Well, we don't have to. Let's just start chugging away. Let's see what we get. So, x0 equals 0. x1, what would that be? Well, it's 0. That's easy. Minus. And now the nice thing is when you plug in 0, most of the terms drop out, except the constants. So we're going to end up with a 9 over negative 9. Well, that's really 0 minus minus 1, which is 1. Aha! That also is not too bad to work with. So what is x2? Well, it's this number 1 minus, now here you're adding up the coefficients. So it's 1 plus 3 minus 9 plus 9. Downstairs, 5 plus 6 minus 9. Now the minus 9 plus 9 cancel. So what do we have? We have 1 minus, upstairs is 4. And downstairs, 5 plus 6 is 11, minus 9 is 2. So it's really 1 minus 2, which is negative 1. Hey, that's pretty nice. How about x3? Okay, so it's negative 1. Our previous guess, minus. Now let's be careful here. We're taking negative 1. Now when it's to an odd power, it's negative 1. When it's to an even power, it's plus 1. So it's negative 1 plus 3 plus 9 plus 9. And downstairs, it's 5 minus 6 minus 9. Okay, so we just put in negative 1. So that's negative 1 minus, okay, what's our fraction? Well, upstairs we're going to get 20. 20. 18 plus 3 is 21, minus 1 is 20. And downstairs it's 5 minus 15, which is negative 10. So minus makes plus. negative 1 plus 2, which is positive 1. Now, we might say, okay, what's the next one? Well, I'm willing to bet you it's going to be negative 1. In fact, xi is going to be 1, and so forth and so on. And you might say, how are you doing those ones so fast? And the answer is, this 1, that's not the first time we've seen a 1. We've seen a 1 before. And so, because we're doing the same process, if we plug in 1, we're going to get the same result. So it's going to be a negative 1 in the next one. In fact, what's happening is we've gone into a loop. So this can happen. This can happen. So it turns out that when you run Newton's method at 1, it says, oh, you should go over to negative 1. And when you put the negative 1, it said, oh, you should go back to 1. So you're crisscrossing back and forth. And so now you're in trouble. So at this point, you can say, okay, Newton's method, it's not going to get you closer to a root. You're just going to keep circling for a long time. So how do you break out of it? Well, the answer is you try someplace else. So you said, don't just start it at 0, try other places. And so if this happens in practice, you really should be sort of following the process. And if the process isn't starting to converge, then something is wrong. And that means you should take a moment, step back, and say, okay, let's start somewhere else. Or maybe we should do a little bit more probing, sample to get closer to the root before we guess. So suppose we started with x0 equals negative 2. Well, what would happen? x1 would be negative 2, because that's our previous guess, minus negative 2 to the 5th. Well, that's negative 32. Negative 2 squared times 3 is 12. Negative 9 times negative 2, that's 18. And 9. Downstairs, negative 2 to the 4th is 16. Times 5 is 80. 6 times negative 2, negative 12. And minus 9. Now, this is maybe as far as we go. Let's see if something nice happens. 12 plus 18 is 30. Plus 9 more makes 39. And subtract 32. Well, that leaves us with 7. So 7 upstairs. Downstairs, 80 minus 12 minus 9. That's 80 minus 21 is, I guess 59? Maybe? Yeah, it's 59. Okay. All right. 80 minus 21. Okay. Well, we're not going any further for sure. But you see, this tends to be a little bit cleaner. In some sense, what's happened here is you see it says it starts at negative 2, and it says, a small perturbation. So usually when Newton's method has small changes, that's the signal. It's like, okay, I'm really close to the root, and I'm really just sort of narrowing in. When you see large changes, that's a sign that either you're very far from a root or something bad is happening. And so this is probably going in the right direction. Okay, optimistic. We'll smile. We say, at least it's looking more reasonable. Okay, and then we'll just say we're done. Done with that one. Okay, all right, well, good. Now, one more thing to talk about. One of the things is almost all of our examples we've been looking at are really of a particular type, namely polynomial. So you might say, okay, so this is all about polynomials. But it doesn't have to be about polynomials. The reason we like polynomials is that they're very easy to work with. In fact, one of the things we're going to talk about when we get to our next course, which is Calculus 2, is how we really like polynomials because they involve the two things that computationally we like to do, namely multiplying numbers together and adding. And when it comes to computation, that's kind of it. That's our big achievement. On a really good day, maybe we'll throw in division. But there's other functions out there. And the ideas of Newton's methods have nothing to do with polynomials. It's all about the tangent lines, its approximation, follow the approximation down. So we can do this with anything. So here's an example. Set up the recursive formula to find the root of f of x equals x minus cosine. So we don't even have to do anything. We just have to set it up. So we just say, okay, our formula says take xn plus 1, which is xn minus f of xn divided by f prime of xn. So for us, we're going to get, this is xn minus upstairs xn minus the cosine of xn. Now downstairs, we've got to take the derivative. So f prime of x is equal to 1 plus sine of x, derivative of x minus cosine of x. So that'll become 1 plus sine of xn. And there we go. Okay, so what's our punchline here? Well, let's start. Suppose you start with 0. Well, 0 is one you could actually carry out, because you're going to get 0 minus cosine 0, so it's negative 1 upstairs over 1 downstairs, so you get 1. Okay, now put in 1. And what do you get? Well, 0.750, 363, ... Probably wouldn't have guessed that one, but that's okay. We used the computer. Now, what's x3? 0.739, 112. See, notice that there was a big jump initially, a smaller jump, and now it's like, wow, the first digit didn't even change. If you go to the next term, 0.739, the first 3 digits didn't change, 08513. So let's see if we can sort of mark this. So here, the first digit stayed the same. At the next step, it was the first 3 digits. Well, how about if we go to the next layer? Well, look how far we're getting here. 739085133. And if we go to the next layer, you'll see here at the 6th iteration that as far as my computer said, these numbers look the same. So in just a couple of iterations, we quickly were able to go from an initial guess of 0 to something which is pretty accurate. So if you had a calculator and was set in radians, it's important that this is in radians, then what you'd see is if you plug this number in to x minus cosine x, it would very likely be 0 depending upon how accurate your calculator is. If it's not 0, it's 0.000000, 7 or whatever, I don't know. Now, there's a different way to do this. So if you've ever had a calculator, and I actually don't have a calculator, so imagine I had a calculator. So here's my fake calculator, and there's an output here. And now, of course, calculators have a couple of buttons. So this calculator has a button that says 0. Okay, so here's my 0 button. And then somewhere else there's a button that says cosine. And then somewhere else there's a button that says equals. I actually don't think this is the place where you would... I don't think they're in the right place. But okay, here you go. So suppose I put in cosine 0 equals. Now what would happen? Well, you get 1. Now, what if I hit equals again? Well, for some calculators it says, okay, what was the last thing you did? The answer was the last thing I did was take cosine. So it would take cosine of your answer and say, okay, well that's 1. Actually, no, so you don't hit equals, you hit cosine. So 0 cosine gets 1. Push it again. Cosine of that. Cosine of that. So you keep hitting the cosine. Now, if you were in high school, this may have been the most exciting thing you did in a math class. But what would happen is you'd start to look at your digits, and they do the following. You start 0, then 1, 0.540, okay, 0.85, 0.65, 0.79, dot, 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 dot. If you did it 50 times, so, pushing that cosine button 50 times, dot, 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 you'd be at 0.739085513. So right here, 0.739085513, but then you'd start to diverge, which means that after only 4 steps of Newton's method, we're more accurate than just hitting this cosine button 50 times. Now you might say, well, what's going on when you hit that cosine button? Well, what's going on is there's a cobweb, and you start at 0, hitting cosine takes you up, that's the output, cosine of 0. Now if you follow it across, so here, this is the input now to the next layer. Go down to the cosine curve. Okay, so this y value, that's if we'd hit cosine twice. Follow it across till you hit the line y equals x. Now hit the cosine again. So these places is where you get after each iteration of hitting a cosine. And what's happening is we're getting closer and closer to our answer, but we're spiraling in very, very slowly. So we'll get the same answer, but with a lot more work. See, this comes back to the idea we mentioned before. It's not enough to know how to get the answer. We want to still be alive when the answer comes out of the machine, or whatever it is that we're using to the computer. And so we're interested in knowing how long do things take. And Newton's method, not only is it beautiful in that it helps us find roots, but it helps us find roots relatively quickly. And there's a lot of beautiful mathematics that happens in doing numerical work, approximation, estimation, and of course engineers, you're going to hear a lot about it in the years to come. All right, that's it for today. And in fact, that's it for this part of the course. So see you on the next part, which is pretty good. All right, take care. Bye.